All right, let's try to make a prediction as to what our graph is going to look like for experiment 1 in the pivot lab. So we have the radial force that is changing as a function of the angular speed, or you could say angular velocity. So what would this graph look like? Let's see if we can do a little derivation. So we know from Newton's second law that the sum of the forces is equal to the mass of the object times the acceleration of the object or system. In this case, what we have is our little cylinder with the force of the earth pulling down, force of the table pushing back up, and the radial force, right, which is the tension force of the string pulling back in. So the normal force and the gravitational force are going to cancel each other out because the object is not accelerating vertically, right? So let's go ahead and eliminate those. So our acceleration is, in this picture, to the right, but it's inward. It's in towards the center of the circle. As you can imagine, the object is traveling. It's kind of a little 3D sketch. Here's the center of the path. It's always accelerating towards the center of the circle as it travels around in this circular path. Right. So we're going to use that net force and substitute it into the equation right here. And then we'll use one more thing we know about acceleration to solve the equation. Here we go. So we have the radial force is equal to mass times acceleration. Now, I'm going to substitute for acceleration. If you are moving, this is looking from above, right, as our object moves around the table. If this is the tangential velocity of the object, the acceleration is inward. All right, that is the direction of acceleration. The value of the acceleration is the tangential velocity squared divided by the radius. So we can actually substitute into this part of the equation. We can say v squared over r. Now, the velocity at which you're traveling depends on two things. It depends on your angular speed, right? How fast you're rotating, and how far you are from the center, omega r. So we can actually replace. V with omega r, right? So I just replaced V with omega r. Now we do a little math. So we say the radial force is equal to mass times omega squared r squared divided by r. All right, one of those r's is going to cancel out, and you're left with m omega squared times r. All right, now what we're trying to do is study the relationship between the radial force as a function of the rotation. Okay, now what that means is we're keeping the mass constant and we're keeping the radius constant. All right, so I'm going to rearrange the equation a little bit. We could say radial force equals mr times omega squared. And what I've just done is I've put the equation in the form y equals a times x squared. Now, I haven't changed anything from the original equation. Not at all, right? All I've done is rearrange its location so I can see that mr is going to be the slope of my graph, and what I should get is a graph that's a squared relationship. So what do we know from a y equals ax squared graph? Well, we know that it would be something like that. Okay, starting from 0, 0. In this case, we would say our y value is radial force, our x value is omega. So this is what our data should show, right? We're going to collect different data points. We're going to keep increasing the angular speed, and what we should see as a result is that force increasing in a squared type of relationship with angular speed. Okay, now let's talk about if we want to linearize the graph, how would we do that? How would we take this graph and make it into a linear, not just linear, but proportional relationship? All right, we're going to linearize it. So what we need to do is take our mr times omega squared, and we need to turn this into y equals ax plus b. Now we don't have a plus b component to our equation. It's just mr times omega squared. So what we need to do is we need to graph not omega but omega squared on the x-axis. All right. So if we graph omega squared, I just realized a mistake I made on the previous graph. Yx. If we graph omega squared instead of omega, and here's the radial force, we should end up with a linear relationship, and the slope of this line, right, the slope of this line will be mr. I made a mistake in the previous graph. Well, let's just digest this for a second, right? So if you linearize it, if you graph omega squared on the x-axis, you should get a linear graph. Now, I made a mistake up here on the previous graph. I said that the slope would be equal to AR, or MR, and that's impossible because M is a constant, the mass is constant, the radius is constant. There is no one slope. If you notice on this graph, the slope is constantly changing, right? So that was not true. You cannot look at this graph and figure out what the slope is. There's more than one slope, right? So that's actually why you have to linearize it, or I should say the benefit of linearizing it. You could still figure out what that a value is by trying different a values until you got a curve that goes through your points, and a lot of programs will do that for you, right? Even Pivot will do that for you. We'll find the closest match. But the other way to do it, the algebra-based way, is to graph omega squared, and then the slope of this linear graph, which is easy to find, rise over run, right, will give you the mr value, right, the mass times the radius, and then you could actually solve for the mass if you know the radius, or solve for the radius if you know the mass.